All right, let's get started, everyone. The screen is not quite right. Let's see. That's Blackboard's. Is that right? What's this doing? I don't know what that's doing. It sounds scary. Okay, that's Blackboard. No, that's Blackboard's. I can't see anything that that's doing.
I think it's Blackboard.
You think it's this one?
Below the chalkboard.
Hello? Dimmer's screen. There we go. That seems very unintuitive.
Where else would you put it?
Yeah. I know, over there by all the other switches. Okay. Good. Pair programming debugging. Glad we found that. All right, cool. Well, now that the screen's working, welcome to class. Big things today. First day of May, which is crazy, and also first day of Module 3. So what we're going to talk about is we're going to start to get into Module 3, which is intermediate representations. So we're going to do a brief overview of various intermediate representations and maybe look at some cases why different intermediate representations are useful. And then we're going to kind of zoom in on our first intermediate representation, which is an AST, or an abstract syntax tree. So how many people have heard of an AST? A few people? People might have seen them be talked about in the PLY documentation, because essentially an AST is kind of the first step you usually take after parsing. And so that's why we're going to talk about it hopefully today, but throughout the next couple of lectures, and talk about how to go from parsing into an AST and what exactly an AST is, and maybe some of the goodies that we get from an AST. Okay, but as always, before we start, let's do some announcements. So homeworks. Homework 1 grades are coming. We're planning on having them out on Monday. So that's the plan. I think we're on track. So expect to see those out soon. Homework 2 was due last Monday, so hopefully that went well. And now we have homework 3 out. And along with homework 3, I provided a reference grammar and first plus sets in the Piazza announcement. So everybody was able to see that? Yep. Okay. And so then everybody's seen homework 3. The nice thing about homework 3 is you have everything you need to do all of it now. Essentially, you're taking that grammar, you're writing a recursive descent parser, and you're using the first plus sets. So what you can do in this homework, this is a little bit of a choose your own adventure. So with the scanner, you can use your scanner from homework 1. If you do use your scanner from homework 1, you have to copy the code in a little bit. There's a few places that need a little bit of massaging, but I suggest that you use the start of string or named group scanner if you want. I think the start of string scanner is a bit nicer because you can more easily add tokens without thinking about how they collide. But you can use your scanner, or if you don't want to use your scanner, you can copy in that exact match scanner that was provided in homework 1. So now you can see that the pieces are kind of coming together. When you implement your parser, you can either use the grammar that you used or that you made in your last homework and your first plus sets that you got from your last homework, or you can use the reference one. And so, you can use kind of the bits and pieces from your previous homework, and at the end you can have a compiler that you've sort of built from scratch. Otherwise, if you don't feel confident in your solutions, you can use the ones that are provided to you, but you have those options. I do suggest getting started on it, as I always do, because it's easier to get help earlier on, especially now that we have all the material. Please have a look at it. It's due on May 9th, giving you a bit of extra time on it so you have time to study for the midterm, which is on May 6th. So midterm is given on May 6th. It's going to be taken during class. 3 pages of notes are allowed, front and back. So the things to study are the slides, the homeworks, and the book readings actually follow along pretty closely with the slides. I do think they're good for study reference. I'm not going to ask any questions that are exclusively in the book. Everything on the test, we've talked about it in class. So I do think the book is good supplemental reading. I do think it's a good textbook. I don't think all textbooks are good, but this one's pretty good. So I do suggest having a look at it when you're studying. It's just good to get a different perspective on things. I'm going to talk a little bit more about the midterm, but does anybody have any questions about the homeworks? All right. In that case, let's talk a little bit more about the midterm. So it's coming up on Monday. There's going to be 3 questions. So the questions are each going to have multiple parts. One of the more interesting things is I will not be here. So I got invited to be on a panel for AI security in San Francisco, which is pretty exciting, but that's where I'll be all day. So Riddick and Sakshi will proctor the test, and some tutors will help out as well. What we did is this room is pretty tight for everybody in the class. I think we have about 110 people. This room seats maybe 120. So, what I want is you to have a little bit of space. Hopefully, you're not going to look at your neighbors anyway, but just to give you some arm room. So what we have is we have this room plus Oaks 106, which I haven't scoped it out entirely, but it should be around here. And that can seat about 30 of us. So what I'm going to do is I'm going to send out an email. Depending on your last name, you will either come to this classroom or 106 on Monday. And then Riddick and Sakshi each are going to be in one of each of the rooms, and then we'll have some tutors helping out as well. So that just gives us a little bit more space. Does anybody have any questions? Yep.
Are the questions going to be free response?
Yeah, they're normally free response. There's no coding questions. It's I don't want you to have to write code on pencil and paper. I think that's pretty awkward. Yeah, anyone else? Okay. In that case, as I mentioned, I'm keeping these study guides in the slides so it's easy for you to find. So it can be in a couple of them. Like I said, anything that we cover in class is fair game. This includes regular expressions, scanners, grammars, and symbol tables, essentially, along with some of the sub-bullets that I have up here. Like I said, there's a chance that a little bit of the material that we cover today and next lecture will be in there, but it's not going to be the main focus of these questions. We've really been focusing on the front end of the compiler. This is regular expressions, parsing, grammars. That's going to be the thing to focus on. And if anything comes in from these from these slides today and next time, it'll kind of just be some pretty basic stuff. And I can populate this for next time so that you can see. Does anybody have any questions or comments? All right, I think you guys will all do great given what I've seen in office hours. It seems like people are on a good track. So, given that, let's go over the quiz from last time. I think it was a fairly short quiz, but we did talk about a new component of the compiler, and that's what both of these questions are about. So error messages about undeclared variables are printed, let's say printed or thrown or caught by what component of your compiler? Are they caught by the scanner? No. Are they caught by the parser? No. Are they caught by the symbol table? Yes. And the back end we have not talked about yet. So does somebody want to kind of explain a little bit what, parsers are where we're catching a lot of these errors. A parser is where we declare them, where we use them. I mean, a scanner is where we even check to see if we have an ID. Couldn't we put a symbol table check in like a token action and say, here's an ID. Let's look it up in the symbol table while we are lexing it. What do people think? Max? Yeah, for the symbol table, you have to know about scope. Scope is something that the lexer or scanner certainly does not know about, because you have to be able to know that you're in a brace, or you left your scope and you popped your scope because you saw another brace. A scanner has a very localized view. It basically says, is this an ID, or is this a number, or is this an operator? And while it can pick out IDs, just the fact that you have an ID isn't enough to know about scope. So then the interesting thing here is that you end up with a little bit of an interplay between the parser and the symbol table, right? Because the parser is the one that parses those braces. It's the one that pushes the scope. It's the one that pops the scope. But when it wants to know if a variable is in scope, it queries the symbol table. So these two kind of interplay with each other, but the scanner has much too limited of a view to catch these sorts of errors. Okay, So the next question was a little bit more of a free response. We looked at some of this last time, and people had some interesting examples. But thinking about scoping rules for Python and C, what are the different ways that the different languages could utilize a symbol table to track variables? And do they use them in the exact same way? Or are C and Python the same in terms of scope? No, we saw some examples last time. Python doesn't even really require you to declare variables. They kind of just appear, and when they appear, can you use them everywhere when variables appear? So if you set a variable x inside of a function inside Python, can you use it outside of that function? No. If you if you make a variable inside of a if you're inside of a conditional, like if you have like an if true and then x equals 5, can you use x outside of the conditional? Yeah. So I find that to be a little bit strange, and I'm sure we've all been bitten by issues related to that. But it just goes to show, in C, if you declare a variable inside of an if statement, if you have, if true int x equals 5, you can't refer to x outside of that scope. So there are differences between these languages. And, these languages are the two most widely used languages right now. So it's interesting that we kind of have the two heavy hitters, and they behave differently related to scope. And, sometimes it's nice, and sometimes it's both of them have their pros and cons. And, if there was one right answer, we wouldn't have more than one language. So I think it's worth thinking about. Does anybody have any thoughts on this? Any experiments that they tried? Any interesting observations? Yeah, Simon?
For loops, I think most of the things where it's like perhaps there's a parentheses in the statement. If you declare a variable in the parentheses before, then that is included within the scope of the statement rather than being outside of the statement.
Yeah, that's really interesting. Because when you have a for and you declare a variable like for int I equals 0, I know we're not handling that in our language, but C handles that. That int is sort of, you can refer to it inside of those braces, even though it wasn't declared inside of those braces. In that sense, it almost feels like a function, right? Because in the function, you declare, or you can refer to your arguments that are declared within parentheses. Yeah, so that's pretty interesting. Yeah?
I think another interesting scope thing is in a lot of functional languages, as well as Rust, you get it's kind of related to scope, but you can redeclare variables with different types, and after that will be treated as if it's that new type. So let's say you have in Rust, let's say you have let's parser equal parser new, and then you after that you want to, for whatever reason, have your output also be called parser. And you can say let parser equal parser.parse, and even if it refers to a different type, that it will now be of that new type, and the old variable you can no longer reference.
Oh, interesting.
Yeah.
So you can kind of like change its type dynamically through the program.
Yes, but you have to redeclare it. You can't just say it.
You have to redeclare it.
Redeclare the variable. Yeah.
Okay. In Python, you don't have to redeclare it, and you can set x equals to an integer and then set x equal to a dictionary, and it will not complain. Yes. So it's interesting how these change. Did I see a hand over here? Yep.
Well, in the example that you had, I think it was like something like int y, and then there's braces, and then like int y again.
Yeah.
I didn't even know you could do, even though I've programmed like a decent amount of C, I didn't even know you could do that, because I think the flags that I use always like prevent me from doing that. So it's just like, well,
Yeah. Does it get?
Thanks for that.
Yeah. It must get caught in the warnings, right? Then with the W wall. Yeah, it doesn't seem like a nice thing, right? Like, and the compiler could easily throw an error. Like, if it can catch those, like we saw in the symbol table, you can always catch collisions. It's when it declares, just check in your symbol table if it's there. You could just stop compiling because it seems like a bad way how to stub your toe. But instead, you're right. You can do it. The language allows it, and yeah, it's kind of weird. Yep.
Is there anything about like pound defines in C, because they work a little differently, where we don't exactly establish variables inside like our main scope or the scope of a function outside of main or something, but they're like even outside of the scope of that.
Yeah, pound defines are macros, and essentially they do kind of a copy and paste of what you define, but they do have variables, right? You can refer to variables, you can bind variables, they have arguments, or you can refer to variables, and in that case it's going to take whatever the scope is. Macros are crazy. They're things I don't understand fully, and there's lots of programming language research on how to do them in different ways, and I think C's are kind of considered fairly chaotic. Other languages do a much better job with macros. Yeah, but that's a good point. Now you have to think about how scope interplays with those, because they're not quite functions, but they're not global variables either. So yeah, and all these rules, when you have to implement like an industry strength compiler, you have to deal with all of those. That's why there are companies that just do compilers and have, I don't know, like hundreds of engineers just doing compilers. Yeah, Joshua?
I just found it interesting when implementing C simple, just deciding on what there's different versions of C. So like there's a version of C where you can initialize the variable within the for loop, and then there's another version of C where you can't initialize the variable, like for I equals 0 versus for int I equals 0. So just deciding on which version of C and then saying, okay, I have to initialize the variable outside of the for loop or inside of the for loop. So just even though it's the same language, it's just a different way of doing it.
Yeah, and it has big implications on writing the compiler, right? Like as a programmer, you might think, oh, that's kind of seems kind of arbitrary. But when you're writing the compiler, if you were able to declare a variable in a for loop, then you have to have rules for the symbol table inside of the for loop and track when that scope actually starts. It starts, when the parentheses open. Yeah, so these decisions that seem like, yeah, as programmers, we might think they're minorly annoying or arbitrary, but from a compiler writing point of view, yeah, they end up having impact. Yeah, cool. Good discussion. Anyone else have any thoughts on scope? Scope is one of these things that programming language nerds really like to geek out on. So if you want to go pick a fight online, you can find plenty of people to engage on this stuff. But we won't spend too much time thinking about it. We just use the simple lexical scope like in C. So, all right, moving on to a new module. What are we talking about? Well, let's revisit, as always, when we start a new module, we're going to visit our compiler architecture. So when we zoomed out, we have our input program. Starts out as a string. We go into the front end. The front end takes care of the parsing. Once we get done with the parsing creates structure. It moves into what is often called the middle end. This is when optimizations happen. And we talked a little bit about this before. Optimizations are not kind of a one-time thing that happens. They transform your code, and then another optimization transforms your code again, and so on and so forth. So you sort of loop in here for a little while, making your code fast, making your code nice, and then you go to the back end, sometimes called the code gen, which produces the executable code, which gives you your binary. So as we saw, this is still a little bit too coarse-grained for this class. So we had our more detailed view. Again, that kind of has to take a detour. But what we're going to do is we're kind of in this area of semantic analyzer. What we're going to do in this class is we are going to sort of move the semantic analyzer more to the intermediate representation. Essentially what this does is this will initially do some lightweight checks on your code. It will do things like type inference and try to make sure that maybe you're not obviously dividing by 0, stuff like that, things that are easy to check at parsing time. Instead, we're going to move those over to the intermediate representation. Part of the reason why is because in our parser, as we've seen, we don't necessarily have a left recursive parser. So what we're going to do is our parser doesn't make as natural as a tree as we might like. So it's easier to operate on the AST. So we're going to move this semantic analyzer over into IR analysis. And essentially what we're going to do is we're going to be living here in this area. We're going to be generating the intermediate representation. We're going to kind of go over that first. And then we're going to talk about different intermediate representations and different things we can do with them. So as a reminder, just to kind of, we're almost halfway through the quarter, to kind of take a checkpoint of where we're at. We start off with a string. The lexical analysis turns that into a stream of tokens. From that, we get a syntax tree. And a lot of times we don't actually make the syntax tree. We said that a syntax tree is a nice visual representation of the computation that goes on, but a lot of times we don't make it. We don't actually make tree nodes or leaf nodes for our tokens. But from there, we go into our intermediate representation, and we are going to be focusing on abstract syntax tree and 3-address code. And we're going to talk a little bit more about that. But just as an example, remember, we had this statement. And hopefully some of this terminology, we said the same thing at the beginning of the quarter, but hopefully some of this is making more sense to you. We have an assignment statement here. An assignment statement is a variable assigned to an expression. From that, the tokenizer, or the scanner, will turn it into a token stream of lexemes. Now, we know that the scanner can just do this. It can eat in this entire thing and give you this stream of tokens. But now we know, because we're implementing a parser, that really you kind of do it one byte at a time as you're parsing. But from the lexer, what we do is we get a syntax tree. And so this is essentially that parse tree that we've been looking at. I'm not showing the grammar here, but this shouldn't be too controversial that this is the grammar that we want. With these IDs, I kind of have an ID label that would map in the symbol table. So we kind of know how to get to this point. This is kind of where we're at in the class now. So we can make these parse trees, or at least we can do computation that mimics a parse tree. Where we're going to go is we're going to take our parse trees and turn it into an AST, an abstract syntax tree. Now, an abstract syntax tree looks very similar to a parse tree, except what we have is, rather than having lexemes be our leaves, we now have what you might call programming language literals as our leaf. We have IDs. We have numbers. Our nodes are no longer non-terminals in the grammar. They're actually operators in the programming language. So an AST, what's nice about it is this is the first step we take from differentiating what's in the grammar. This is how we define the grammar of the language, into the program meaning. Each of our nodes have meaning. Multiplication means multiplication here. Of course, we saw that, up here, we could kind of squint at it and say, this is 3 times 60, and this kind of means, we eventually want it to mean multiplication. Here's where we kind of solidify that, because we actually have a node, and this node is only for multiplication. This node is only for addition. So we're going to talk a little bit more, but, squinting at them, they do look similar. And that's good. That's a good thing. We want every step in our compiler. Compilers are complicated beasts. We want every step to be sort of, not too difficult conceptually. And so this first step from parse tree to AST is kind of going to be the first one we take. Yep.
So just to get some perspective, is the syntax tree, is that more about classifying the operations, and the AST is more about implementing those operations?
I like the word that you use there. AST gets you closer to the implementation. So it's a step along that path. The syntax tree comes from the grammar. So essentially, this syntax tree would come from you being able to write a program like this, like position equals initial plus rate times 60. You could maybe write this in something like, you could write it in like an S expression. If for those who know S expression, that is, you do plus, plus initial times rate 60, something like that, like a prefix notation. There are programming languages that you do write like that. Very famously, old HP calculators had this. You can still find them on eBay. Although people who used to use them will not give them up easily. Also, Lisp, languages like Lisp, you have syntax like this. So your syntax tree is going to be related to the grammar. Your syntax tree for something that looks like this is going to be different than something that looks like this. However, both of them should produce an AST that looks like this. Basically, syntax tree is tightly coupled to your program grammar. It's what your programmer writes. Your AST then is caring less and less about what the programmer wrote and what the program means. Does that make sense? Okay. So, as sort of to look a little bit more ahead and thinking about where we're going, what's really nice about the AST is you can do some analysis on it. So this is where we're going to start to do some analysis on our AST. And one thing that you can start to do is what's called type inference. Now again, there's a whole branch of computer science on type inference. People get really into it. It's very fascinating. we're going to keep pretty basic but still do useful things with it. What we might have in this equation, because this is kind of a physics equation, you could imagine that these are all floating point values. However, the programmer wrote this as an integer. Now, in some languages, you will get yelled at. It will say this needs to be a float, and so you might try 60.0, and then you might get yelled at again, and it'll say it needs to be, that's a double, and so you need to add f. But languages like C and like Python, they'll let you write this, but underneath the hood, your hardware is not capable of multiplying a floating point number by an integer. If you feed the bits that represent those two types into the machinery that actually does that multiplication, it's going to be undefined. What you need to do is, behind the scenes, your compiler needs to convert this 60, that is an integer. The programmer gave you this as an integer. It needs to convert that to a floating point value. It needs to get the bit representation of 60 into float. So the compiler behind the scenes will do an integer to float conversion, and then it can do that multiplication on a floating point multiplication unit in your hardware. So this is where the compiler will help out the programmer quite a bit by doing these automatic type conversions. So we call this type inference, and we're going to see more of that throughout the lecture. So that's what's really nice in being in a tree form like this is we're going to see the algorithms for doing type inference are quite nice. From the AST, another nice thing is that we can convert our code into what's called a linear intermediate representation. A linear intermediate representation looks like a program. It's linear because it's just some simple instructions in a row, and you execute it like you would like an assembly program. So we oftentimes call it 3-address code. That's kind of the terminology is from classic computers where registers were addresses. But really what 3-address code means is usually instructions only have 3 registers, the destination and 2 operands. But you can see if you have this AST, if you do a post-order traversal, and if you make new registers for every node, then you can get this program here that looks close to assembly but not quite. And we're going to talk about some of the differences there. But again, it's this idea that you want to take baby steps to get where you want to go. So from a syntax tree, AST. From an AST, 3-address code. And from a 3-address code to assembly. So again, at every step, you want them to be simple, and you want them to kind of, look like they're not that big of a change. So, like we said, intermediate representations, we have several forms. The first form is a tree, the abstract syntax tree. We're also going to see graphs. Graphs are really good for optimizations, and those are called control flow graphs. How many of you have heard of control flow graphs? Okay, exciting. We got new stuff. Okay, so that's going to come up maybe in a couple of weeks. And then we have linear programs, which are essentially those 3-address codes, those things that look very similar to assembly. And the thing is about, this is in compilers where things might get a little bit messy. Sometimes your code is represented as a hybrid. Sometimes it's a graph where the nodes are a linear program, or maybe a linear program where expressions are ASTs. The idea here is that you want your code in the easiest possible form for you to analyze it and do optimizations. Maybe you're checking for memory safety. Well, different formats for the code are going to be easier or harder to check. If you're doing type inference, you usually want a tree. We're going to see several optimizations that work better in different forms. And typically the progression throughout the compiler starts close to a parse tree, like an AST, and it moves closer and closer to an ISA or a binary form, like the 3-address code. And so, again, we can actually see some of these intermediate representations in the compilers that we use. So Clang, which I think is a pretty great compiler, Clang is kind of the front end for the LLVM compiler suite. And one of the big things that makes LLVM so cool is the LLVM IR, or the LLVM intermediate representation. So it's an intermediate representation and a specification. Some of the things is that it gives you unlimited registers, but it really just kind of has very simple expressions. So if you take an example of an expression that can be, kind of hairy, here's the quadratic formula. It's something we all probably learned a long time ago. I wouldn't be able to tell you what it is off the top of my head, but I looked it up on Wikipedia before class. We can write that in something like C, right? We can basically translate this down. We don't have a plus or minus, so I just picked minus. But we can write down this complicated math form, like this. And you can get pretty close to doing this in C simple. But when we go and look at how this might look in an intermediate representation, what you can do is you can compile with Clang. And yeah, what's really nice about Clang is you can tell it that you want to see the different steps that it's taking. So what I did is I told it emit LLVM. And basically what that says is rather than giving me a machine code binary, show me your intermediate representation that you created. And so this over here that we're looking at right here is LLVM intermediate representation. And you can see that the instructions are fairly simple. We have a floating point negation. We can probably assume that that's this negative b. We have a floating point multiplication with 4.0000. So that's going to be a floating point multiplication here. And you can see that, this looks like assembly, but it does seem to be a little bit easier to read. I don't know. I think it's easier to read. What do people think here? Yeah. What are some differences that we're seeing between this and maybe assembly? Yeah.
I guess it has the percent sign number and then equals for almost every line.
Yes, that's really interesting. We have this percent sign number here. What this is essentially doing is making what are called virtual registers. So these are kind of like variables in your program. So you can have as many of them as you want. So you can see up here, we've gone up to like 23. And if we had a more complicated program, we could go up to hundreds or thousands. But yeah, we're assuming that we have unlimited registers here. We will eventually need to transform this into code that uses the finite registers that you have on your machine. But because you're allowed unlimited registers, you don't have to worry about shuffling registers around, dropping them to memory, and so on and so forth. So I actually think it makes it, not too bad to read. You don't quite get the messiness that assembly has. Anybody else see anything? Max? Yes. So LLVM has types. You can see that it's loading a float. It is doing an F multiplication, which stands for floating point multiplication with float. When you are down in assembly, do you have types? You have bits. So you have zeros and ones, and that's the only types, and you have to manage them. So LLVM has decided to keep types here. We won't keep types in our intermediate representation for your next homework, but yeah, it's a nice thing to have around here. Joshua?
I noticed there's exclamation marks, and then I don't recall assembly having them.
Yeah, what this is this is essentially meta information. This is debug information. So what this is doing is tracking what I think it's line number. I think this line number looks really large because we're including a math header. But yeah, it's tracking extra information that's going to make it easier to debug. And also align information is extra hints to the compiler to talk about memory. If you have certain aligned accesses, you can do more efficient instructions in the back end. So yeah, you're tacking on extra information that can be used later on in the compiler. So yeah, this is a bit different, but hopefully you can see that this seems like a good stopping point on your way to assembly, right? And what's nice, like I said, Clang, you can just go and for any program that you want, you can ask it what its intermediate representation is, and it will give it to you. So that's probably the most famous intermediate representation being used right now. For some of the compiler folks in the class, does GCC have an intermediate representation? Does anybody know?
I don't think so.
So it does. It's just not documented very well, and they don't want people touching it. It's sort of that's why we don't really hear about it, because they sort of want a hands-off approach to it. Basically, any sufficiently complex compiler will have an intermediate representation, But one nice thing about LLVM is it's really just opened its intermediate representation up and said, we're going to build the entire compiler on this, whereas GCC keeps it hidden away. And part of that is due to its licensing, which is kind of an interesting intersection of culture and technical components of computer science. Okay, so that's kind of our 3-address code. I want to look a little bit at some different representations of code and think about optimizations, and we can see how different representations of the code might be better for different optimizations. So one of my favorite optimizations, and yeah, if any of you have taken any classes with me, we always talk about this one, is loop unrolling. So let's actually get rid of this print. So who knows what loop unrolling is? A few people. Who wants to explain what loop unrolling is? Say, oh, do you want to go?
Sure.
Yeah.
So when the loop is compiled to assembly, if it's a tight loop like that one, it will do x equals plus 1, hit a branch, go back, do x. So branches in assembly are slow, so loop unrolling is a technique that says, hey, on every step we're doing x equals plus 1, why don't I just take that and then do that like 10 times and then check the loop condition.
Yeah, exactly. So yeah, if we think about how this code executes, we go, we increment x, we loop back, and when we loop back, there's a few things that happens here. We check the condition. We check to see if I is less than 100. If it is, we go into the loop again. Otherwise, we branch. Otherwise, we increment. So what you can do is you can actually get rid of this. You can get rid of a couple of these checks. And the way you can do that is if you do an update in here, I equals I plus 1, and PowerPoint is really annoying. And then if you do x equals x plus 1. So we've changed 2 lines of code here, but we've really saved a decent number of operations, because what we've done here is we don't do this check. We do this check half as often when we're going around. But because instead what we've done is we've incremented the variable inside the loop and just gone ahead and done an extra loop. What are we assuming here? Why aren't all loops written like this? Jacob?
We're assuming that the oh wait, no, this is a different way. Never mind.
Okay, no worries. Anybody see? Cameron?
Is it the fact that you don't have any dependencies or whatever? Like it's not based on like previous loops.
Well, you can do loop unrolling even if you have dependencies, just as long as you don't reorder within the loop. But we are going to talk more about that later. Yeah?
We're assuming that we're not going to jump straight from 99 to 101, skipping when I equals 100.
Exactly. What we're assuming here is that we do go around this loop an even number of times. Because basically what we're doing is we're saying we are doing 2 loop iterations at once. We're doing 2 loop iterations half as many times. That's what this is saying. And because we're doing 2 loop iterations, we need to know that this loop is going around an even number of times. Otherwise, we're going to do an extra iteration. So when you do unrolling, however many times you unroll, we could write the code to unroll an extra time. But would that be valid? I've seen some nods. No, because now we're doing 3 loop iterations. We're only checking every 3 iterations. And 3 does not divide 100 evenly. So what that means is we're going to basically do 102 iterations before we catch this. So when you do loop unrolling, you have to make sure that the number of times you unroll evenly divides your loop bounds. Yep?
I feel like, or just intuitively, it feels like it should be based on whether you can replicate the input of the original loop more than an even number. Or is it just, or are you just saying for this case we need an even number?
For this case, we need an even number, yes. But the general condition is a little bit more abstract than this. Yeah. exactly. But so you can actually end up saving a decent amount. And what's cool, what I really like about loop unrolling is, like, let's say this was legal. So let's say this was 102. So let's say we were able to unroll this 3 times. What that also does is, if we were to look at this code, we as humans can see that we can probably optimize it even more, right? We can say this is I plus 1, I plus 1. We can just get rid of one of these and do, I plus 2. Like, that seems like a pretty easy optimization we could do. And we could, roll all of these x's, and we could say x was x plus 3, something like that. And so what loop unrolling does, and at this point, we've saved a bunch of comparisons, and we've saved a bunch of addition operators. So loop unrolling is not just about saving comparison operators. It also presents a window to do further optimizations. And you can really, allow the programmer to write very simple code, and then the compiler can make it very fast. Let's think about how a for loop might look. So in a tree form, like in an AST tree form, you might have a for statement, like what you've done in your homework. And this for statement has an assignment statement. It has a comparison. It has an update. And then it has a statement in the body. This is essentially what your parse tree is going to give you for your for loop. And changing it to an AST is not that difficult. So then what you could do is, if you have this tree form, having the tree form of the code for a for loop statement, it makes loop unrolling pretty straightforward. You have to do some of your analysis. You have to find your iteration variable. In this case, it's I. So you'd go find the variable that gets incremented. For that, you just check your assignment, you check your comparison, you check your update, you can find I. You check that your statement doesn't do anything weird with your iteration variable. That allows you to determine how many times your loop goes around. And then you check that your comparison, in this case, goes around an even number of times. And these are all things that you can do because your program is broken up nicely into this tree. You know these components. And if you do that, then to apply the optimization, it's super easy. You just take your statement, you add an update and a statement to it, and then when you lower this to code, you will get your update and statement. And so having these nice boxes in tree form makes loop unrolling actually like a really easy optimization to do at this point in compilation. Now, if you compare that, if you took that simple for loop that I had, and if you gave that to LLVM and you said, give me your intermediate representation, your 3 address code, the one that's closer to assembly, your for loop ends up looking like this. And if your for loop looks like this, you have to go and you have to try to figure out where the assignment is. You have to go and try to figure out where the comparison is. You have to go figure out where the update is. So if you're going to do optimizations like loop unrolling, you want it to stay in a tree. You don't want to go down here and try to do loop unrolling in a form like this. On the other hand, there's another very common optimization called common sub-expression elimination. If you have something like z equals x plus y, a equals b plus c, and d equals x plus y, can this be optimized? Yeah, pretty easily. You're doing x plus y twice. X plus y is in z, so you just put c there. You can remove that redundant addition. Now, these sorts of optimizations, where you do this common sub-expression elimination, they're really nice to do in code like this because you do see those individual operations. You see what you plus, you see what you multiply. And so in this case, you want an intermediate representation that looks more like the LLVM IR. So like I said, intermediate representation, you get a lot of freedom here choosing which intermediate representations you want to have. The design choices end up being you want intermediate code or intermediate representations that look close to your previous stage and get you closer to where you want to go, and then you want to optimize them based on what is patterns that are easy to identify at this using the representation that you're at. So in that spirit, our first intermediate representation is going to be an abstract syntax tree. This is one step away from parse trees. It's a really good representation for expressions, And the analysis that we're going to end up doing on it is going to be doing type checking and inference. And, again, I like to show you guys that for all of these representations we have, you can just go to real compilers and they will tell you about the AST. So in Clang, you can just pass this command line flag. And over here, this is one intermediate representation. This is the LLVM IR. But what you can do over here, and I'm going to comment out the math.h because otherwise we're going to get too much output. We can just we can dump the AST. And what you'd see over here is in the output, it's, reading a tree in text form is not the nicest thing, but what you can see is, here's an AST and here's a binary operator, and this binary operator is going to be equals, so that's probably this equals. Here's a float with a binary operator of, let's see, divide, so it's going to do the division next. So if you kind of go down the tree here, Clang will give you an AST of whatever program you give it. And if you were to kind of work through this, you would see essentially something similar to the parse tree that you would get for this expression. So, all of this stuff is actually in the compilers that we know and love. Let's talk about what an AST actually is. We kind of talked about it already. So what we're going to do is we're going to start by looking at our parse trees. So here's a very simple grammar which has expressions, terms, and factors. It's just plus and multiplications. And if we have a simple input like this, 1 plus 5 times 6, what you might say is, in the parse tree, what are our leaves? Well, our leaves are the lexemes. So the leaves are the lexemes in a parse tree, and our nodes are non-terminals. We have expressions, terms, and factors. So, a parse tree is really just totally defined by the grammar, lexemes and non-terminals. And then the other thing about parse trees is a lot of times they're not explicitly constructed. Like when we do our parser, like your homework that you have out, we're not actually going to build a parse tree. But the computation that you do will follow the parse tree structure. So parse trees are good representations, but they're not oftentimes explicitly built. ASTs, on the other hand, here's an AST for the same computation. Again, if we look at some differences, the main difference is that this is now disjoint from the grammar. We don't care about what the lexemes are. We don't care about what the non-terminals are. Instead, our nodes are going to be operators. This plus actually means plus. It's arithmetic. This multiplication means multiplication. Our leaves are primitives in the programming language. In this case, they're numbers. They could be variables. But we've really taken our first step away from the grammar, and I'd say unless you're carrying meta information to help with debugging, we are now decoupled from the grammar. I don't care how you get here, but this AST really encodes 5 times 6 plus 1. The other thing is they're oftentimes more compact. I think we all can appreciate that. The parse trees ended up getting a bit unwieldy, especially as you got multiple levels, you ended up getting these long sticks. Parse trees or ASTs don't really have to deal with that. And one nice thing about ASTs is here's a more unwieldy parse tree. This time we put parentheses around the 1 plus 5. So we put parentheses around 1 plus 5. We do that in our grammar so that the addition appears lower in the parse tree so that it gets done first. But that addition is all the way down here because we have to go down this stick of term, factor, get our parentheses, expression, and then we have to go down this stick again, expression, term, factor, num. So this tree ends up being, I don't think it's very nice. For such a simple mathematical expression, this is kind of a big tree. Well, in an AST, that shrinks up just to this. Now, did we lose our precedence? No, we still have plus lower in the tree, so we still are going to do this plus first, but we've been able to drop all of this baggage of the parentheses, of expression, all of these long sticks, because these sticks are really just there, and these parentheses are really just there as a byproduct of the grammar of the programming language. We don't necessarily care about the programming language at this point. We care about the computation, and the AST can encode that computation in the most succinct way possible. Okay, is that making sense? Okay, so let's do a bit more formalization, because we will be building ASTs in this class. An AST is a tree-based structure. We're going to use it to represent expressions. And our main building block is a node. So our leaf node, at least for C simple, is going to be an ID or a number. We're going to have some nodes that have one child. If you have one child, those nodes can be like a unary operator, like a negation, or it can be a type conversion. We're going to be doing a lot more with type conversion in this class, like converting an integer to a float. And then we're going to have quite a few nodes with two children, like a binary operator, like a plus or multiplication. So not too hard to write in Python, and in fact, we can use object-oriented programming to make this not so bad. So our base class is an AST node, doesn't really do anything. But over here for our leaf nodes, we can have a leaf node, has a value, and a number. A number can be a leaf node. In that case, you don't really have to change what a number or an ID is. Eventually, we will want to tack on information to numbers and IDs, such as their type. And then over here on the binary side, you can have a binary op that is an AST node, and that just has a left child and a right child. And then, for example, we can have a plus node and a multiplication node. And really what we're doing here is we're just using the class name to differentiate them. This is an object-oriented way to kind of construct a tree. Additionally, you could have a binary op node and then just have a class member that says, hey, am I an addition or a multiplication or whatever. But this is just one way how to do it. Okay, so we have some of our nodes. And again, we can use object-oriented programming to make our different types of nodes. And let's talk a little bit about how to make an AST from a parser. And some of you saw this in Ply. I think part of the Ply documentation actually says how to do this. But in order to do that, we're going to have to talk about parser actions. So remember, we talked about token actions. Token actions were a piece of code that executed every time you matched a certain token. Well, parser actions are very similar. They perform an action each time a production option is matched. And typically, they're performed after the entire production action is matched. And they can be useful for making a parse tree, but also useful for catching errors early on. So for some of you, and some of you that played around with Ply a little bit more, this was sort of built in. What happens is, if you have a grammar rule for a declare statement, where you have a type followed by an ID followed by a semicolon, like you all probably did in the homework. What you would do as a parser action for this is you'd want to store that ID in the symbol table. So what you can do is you can refer to the result of your different symbols in this rule. So for example, I'm going to say $1 refers to the type, $2 refers to the ID, $3 refers to the semicolon, and then you can use the results of those to perform an action. So for example, in a declare, we'd want to insert that ID into the symbol table. So you'd say symbol table, insert, $2 is going to be the ID, and probably you'd want to keep track of the type. So maybe you change that to $1, depending on whatever you're storing in your symbol table. So parser actions, the idea here is that you get these arguments that get passed in. Every textbook refers to them slightly different. I'm just using $signs here. But we'll say which syntax we're using as we use it. So, for example, if you come here and if we have here's a simple expression language, it's just pluses, minuses, and parentheses. If we were to do a production action for this option where we're printing, we're going to match this option and we're going to do something after we match it. If we print, let's say we just want to see what comes in $1, what are we going to see? Well, if maybe an easier question is if we print $2. If $1 refers to this, $2 refers to this, $3 refers to this, what are we going to see if we print $2? Probably just a plus. Yeah, that's a terminal. If you print a terminal, that's just what you're going to get. But if you print 1 refers to an expression. Well, this is a production option for an expression. So what goes on here? Well, what happens is, this is, I guess, slightly different than the token actions, is that every production action has to return something. So, for example, if we were to return the string expression, and let's say we just returned expression here as well, then what happens is when you do the production action here, this is going to get whatever the expression here, this expression required an expansion of one of these rules. Maybe it was a unit, and if it was a unit, then the unit has to return something. Well, what does a unit return? Well, whatever it matched in this rule, whatever it matched in this rule. So every production action has to return something, and it's essentially returning something to its parent. Remember, think about these things as like a parse tree. So you're essentially returning a value, and we're going to see this in action. So if we wanted to build a calculator, and some of you saw this in Ply, it's actually not too bad. What you could do is, if you're a number, you just return yourself. That's just $1. And if you're in Python, you might need to cast it to an int or something like that. If you are an expression surrounded by parentheses, well, then you just return whatever that expression evaluated to. So I'm just going to say return $2. I'm going to say return int1. Do the parentheses actually do anything for us? Do we need to, when we actually are evaluating this, assuming we only have numbers so that we can evaluate this, do the parentheses actually do anything for us? No, the parentheses were there to enforce precedence. Precedence comes out of the tree structure. So we're going to get that precedence automatically just by the fact of parsing. So we don't actually have to do anything with the precedence here. So a unit, again, we can just return whatever that unit is. And then if we have a subtraction, we can just return 1 minus 3, right? Because 2 is this one. So we just return whatever this expression is minus whatever that unit is. And again, this is all recursive because whatever this unit is, eventually got returned from this unit, and that unit was either an expression in parentheses or a number. And then similarly here, we can return 1 plus 3. Right? So we can use these production actions to essentially do computation during parsing. Now, the nice thing here, and if you want to go play around with Ply, it's in the documentation. It can be kind of fun. If you only have numbers in your language, you can essentially make a calculator, and you can evaluate whatever that expression is while you're parsing it. And you do that just like this. However, programs oftentimes have variables, and you don't know what the variables are at compile time. So because of that, we actually need to, instead of actually evaluating things at parse time, we need to build an AST. So let's see. So if we want to build an AST, so here's a slightly more complicated language. Here we have expression, terms, factors. But keep in mind, we also have our AST nodes that we defined. If we want to build an AST using parser actions, what we're going to do is we're going to basically construct these, and we're going to pass them up. So what I'm going to do is I'm going to show this here, and then we'll walk through some of them. So if we have an ID, we just return an AST ID node, and we put the value of the ID there, so we can keep track of its name. If it's a number, we make an AST number node. We just include that number. Otherwise, if it's an expression in parentheses, we said that the AST doesn't care about parentheses. They all kind of get sucked up and compressed. We just pass along whatever we got, so we don't actually have to record the parentheses. Similar with those sticks, a factor is just sort of taking that stick down in the parse tree. We don't actually have to do anything. We just return whatever that factor was. If we have a multiplication, we return an AST multiplication node. And what are our children? The children are whatever node that is, whatever node that is. Same with plus. When we see a plus, we make an AST plus node with whatever this expression is, whatever that term is. So if we build the AST, if we have something like this, parenthesis 1 plus 5 times 6, this is our parse tree. And if we start building an AST, we come down here. We see num. Num is 1. So let's see. In an ID, we're going to have an AST ID node of 1. So we're going to say this is an ID 1. So that's going to be an AST node that we construct here. We're going to bubble up. It's a factor. So factor just returns this AST node. So this AST node just keeps getting returned. Term. This is the single argument term. So term is here. We just return this AST node. So this AST node keeps bubbling up here. And now we have plus. We're going to bubble up here where this AST node is going to be returned in this expression for plus, but we don't have all the arguments. So that means that we don't actually do this production action until we have the right-hand side. So let's go down on the right-hand side. Right-hand side ends with a num. So that num is going to make an AST node. An AST ID, this is num 5. This is num as well. Okay, so we get our num. That's a factor. The factor just returns whatever this AST node is. And now we have these AST num, and now we can do the production action for the plus. The plus makes a new AST node with 1 and 3. So this is 1, this is 3. So now we get an AST plus. This is always painful to do in PowerPoint, but I will try to still little branches here. Okay, so this AST plus is what gets created from this expression right here. Because we had R1 and we had R3 from over there. Now we bubble this up and we have our parentheses. Let's see. So that expression here is this one. So now we launch this rule. This rule, again, we don't care about parentheses, so we just return this node. And this node,